Hi, everyone, and welcome to this edition of the Humans of AI podcast, where we are focusing on the humans behind the algorithms. This episode of the Humans of AI is sponsored by Core Intelligence. Core Intelligence specializes in all things machine learning related, specifically dashboards, natural language processing, your standard classification problems and prediction problems too. If you have a problem that either requires any of those aforementioned things, Core Intelligence can probably help you out. So feel free to check them out at www.coreintelligence.com.au if you have any thing along those lines. So today, I was lucky enough in today's episode to interview Stephen Hogg. Stephen is the principal machine learning engineer at Isentia here in Sydney. And he also helps run the Sydney Natural Language meetup, in the Sydney NLP meetup. So he has a lot of experience in the NLP space. And I was lucky enough to actually meet him at the Amazon Summit, where we got talking about transformers. And I mentioned to him, would you like to do a podcast? And he agreed to it. Transformers is a technique that I'm not very familiar with yet. And I thought it would be cool just to meet up and try break apart just exactly what's going on with transformers. And, this has got a lot to do with the recent work from OpenAI in their GPT-2 model, the T, and that stands for transformers. So I really hope you enjoy this episode of the Humans of AI. And if you like this episode, don't forget to click or subscribe to your favorite podcast provider. So enjoy. How's it going, Stephen? Thank you so much for doing this, mate.
Thanks for having me. This sounded really fun, so I was really keen to take you up on it.
Yeah, we met at the summit, and I mentioned that I was starting a podcast. So just to introduce to everyone who's listening, Stephen is the principal machine learning engineer of Isentia.
Yeah, it's a pretty fun job. We're the largest media monitoring company in Southeast Asia. We're based here in Sydney, and we've got a wide range of really problems to work on, which is kind of why I wound up here.
Yeah, cool. So the reason there's a reason, there's a big reason, but the reason is transformers. But we'll get to that in a second.
Yeah.
But before we get to that, you also have a lot to do with NLP, yeah?
Yeah.
Okay. And you run the Sydney Natural Language Processing meetup, I believe.
Well, I'm one of the people that does, yeah. Cool. There's a couple others on the administrative committee as well. There's a guy called Ben Hashi and a guy called Bill Radford.
Yep.
And then there's also Adam Schuck and Sharon Liu.
I think I've met Adam. He's a top-notch bloke.
Yeah.
Cool. I don't know if you want to share with everyone, but you had a really great transformer joke.
Oh, yeah.
I think it's a good way to kick this off.
Yeah, I mean, if we start at a low point, then that makes sense. So a month or two ago, someone was presenting at our group, Sydney NLP, and they were talking about transformers and how they work. And so I got to the point where there was questions, and I decided to break the ice a bit by asking them something to do with, well, if you look at the circuit diagram for these transformers and these really complex models that you get now, they look actually like a probabilistic graphical model. So are we actually just solving the problems that used to be related to them, or are there, when it comes to these transformers, more than meets the eye?
Hint.
Yeah. I was really happy with that joke because
Did you come up with that on the fly or?
Yes, I actually did. And then 5 people got it. And then about another 30 seconds later, everyone else got it, which is my preferred type of terrible joke.
That's the best. That's the best. There's some thought involved.
Yeah.
For anyone listening, do you want to drum roll drop the punchline?
Yeah.
30 seconds has passed already and someone might not have got it yet.
Yeah, it's the theme song from Transformers, obviously.
All right. Cool. On that high note, so today, one of the main reasons when I met you at Summit, I would love to
to talk to you about transformers because it's something so that's a type of machine learning model, something I haven't got around to yet. There's so much to learn. And it'd be awesome if you could share your knowledge and what you've learned playing around with them yourself. Okay, so I think we were playing. There was a new tool that was released on Thursday, I think it was. I can't remember what it's called again. Just bringing it up here. But you get to play with GPT-2 live.
Oh, really?
Yeah. Have you not seen that yet?
I heard about it vaguely through yourself in an appropriate slope. I hadn't actually. That's one really good way of discovering things. Just like people tell you about them.
Yeah.
I haven't actually gone and played with it myself. The completions I saw you and others creating though were terrifying.
Yeah. It actually is insane. It's next level.
Yeah.
I'm bringing its name up right now. I believe it's called. talk2transformer.com. That's all one word.
Okay.
Yeah. We were auto-completing, put in 5 words and to try auto-complete stuff around Game of Thrones because, George R.R. Martin hasn't finished the series yet. So we're trying to get some models to finish it for us. But okay, so moving on to transformers, what's going on here? Can you start at like maybe a high level and then dive down a bit more?
Yes. So the thing with transformers is that once you've gone through enough background and understood all the things that lead up to them, they're not that complex to understand. I think, that's the problem because you've got to push yourself through all that first. The other thing is that a lot of the explanations of transformers I've seen out on the internet basically consist of here's a circuit diagram for a neural network. Okay, now it's obvious.
Yeah, exactly.
Not to like diss the people that are doing that because that stuff still needs to exist.
100%.
But there's actually a reasonably simple concept at work. Do you mind if I go reasonably far back in history and start off there?
This is your oyster. Go for it.
Okay. So I'm going to go really, really far back in history to LSTMs, which is like all of 10 seconds ago in any other field but AI and machine learning.
Old Schmidt-Huber.
Yeah. So going back a while, we've always been trying to figure out how to solve this thing called a sequence-to-sequence problem, which is where you have an input that is a sequence of things, so the order in which they appear matters, and the same for an output, which you're trying to predict. Now, a lot of the time when you think about this, so translation is a classic example, it's really tempting to subconsciously view these two sequences of like something in English, I want to eat pudding, and whatever the equivalent is in any other language, as being contemporaneous. But that's not the case. And that's actually a really important nuance. So when we first tried to solve this problem, we used LSTMs because like you can encode long distance, things of interest, and that seems important. The problem with that approach was that like you get to the end of your input sequence and all the information you've learned gets pancaked up against this invisible wall between the end of your input sequence and the start of your output sequence. So like that was the limitation there. Does that make sense so far?
So what's the wall?
So the idea is when you're training or using one of these models, what you do is you feed in your input sequence one element at a time, and then a special character that says, okay, that's the end of the input. And then from then on, you try and predict an output sequence. And so you can predict the first word given everything you've learned up to that point in time.
Yep.
Then your second prediction is dependent on the first one, and the third is dependent on the second, and so on and so on. And if you've done any time series work in the past, you'll know that the further you predict into the future, the more the errors of your model open out. And so there's kind of that problem there where one, the very last encoding that you output from the very last element of your input sequence has to tell you everything, not just about that point in time, but everything that came before and the relationships between them, which is already overloading this one poor thing. But then second, you've got this problem of, okay, once I've made my first prediction, then I'm well and truly in no man's land because my second prediction is dependent on whatever my first one was. And if that wasn't good, then not only are things already bad, but they're going to get worse.
It's exploding error by the sounds of things.
Yeah, that's precisely it.
Yeah.
So those two problems meant that LSTMs seemed promising, but they didn't quite solve this issue. And so that's where this thing called attention comes in. Right. And so what attention is basically it's basically a cross product. Like get every element of your input sequence, allow for there to be a relationship between each of them and every element of your output sequence. And then that might solve this second problem and potentially the first one to boot. We hadn't quite abandoned LSTMs yet. So what we wound up with was for translation, among other things, this paradigm known as encode, attend, decode, predict.
Okay, so can you depack that a little bit?
Yeah, okay. So imagine you've got an input sequence. Now, the first thing you want to do is transform each element of that input sequence into something that is more useful for the task at hand.
Okay, okay, yep.
And so you use an LSTM layer to do it.
Yep.
And not only do that, but do that in a way that, in some sense, takes account of the sequence elements before and after it.
Yep.
And then once you've got that for your input sequence and your output sequence, because you do the same thing with that, you kind of mash it through an LSTM and provide a slightly different set of values for each element in your sequence.
Yep.
Then you want to find the relationship between every input element and every output element using this attention mechanism.
Right.
And so that worked all right.
Oh, have we got to transformers yet?
No, we're still getting there.
Yeah, right. So circa what year are we talking now?
Not that long ago.
Okay. 2017, 2016?
Yeah, something of that order.
Yeah.
Which is still like not that far after
I know.
LSTMs. But anyway, doing machine learning is so bad for your attention span. It's worse than Twitter.
I know.
Anyway, so we've got this model where we have an input sequence, we transform it into something more useful using an LSTM, and hopefully in doing so, each element of the sequence starts to have context beyond itself embedded in it.
Right.
The same for each element of your output sequence. Mm-hmm. You encode it using an LSTM, maybe a bidirectional one, whatever. And then you get the cross product of those two things to try and marry up both ends.
Okay, yep.
Okay. There are still problems here though. One is that LSTMs are slow. You can't process the second element of your input sequence without processing the first one, because that's the way an LSTM works. The idea is that it has to take information from past, have it in an internal hidden state, and then marry that up with the current input in order to produce something new.
Okay.
So,
yep. Got you. You got you. I'm following you.
Yeah. Okay.
I've seen like the diagram of an LSTM, so that kind of visualizing that right now. But
yeah. So the idea is that basically you take input number one in your input sequence, run it through your LSTM. It somehow conceptually stores what it's seen in a hidden state. And then you do the same for element two, but then that hidden state contains stuff from a previous time step.
Yep.
And so that's where this like dependency comes in, where you can't just take your input sequence, smash it through some matrix algebra, and then you've got the encoding. Mm-hmm. So there was that problem. And we wanted to make it faster because making stuff faster means we can throw more data at it. Mm-hmm. And that's kind of what transformers are. So if you take the input encoder, which is an LSTM, and you take the output encoder, which is also an LSTM, mm-hmm. and you replace each of them with a weird form of attention in their own right.
So you're getting rid of the LSTMs.
Yeah. So what I'm going to do is replace the LSTM that I use to encode my input.
Yep.
With a form of attention.
Yep.
It's called self-attention, where basically you have to reproduce what you've seen.
Yep.
And I do the same for the output encoding step. Then that's actually a transformer. So instead of encode, attend, decode, predict, what you've got is attend, predict. And so the idea is it's a slightly different version of attention. Because sorry?
It's just fascinating. Like, again, I've yet to dive down into this, and like, so I don't want to make any like newbie questions, but honestly,
is any of this not making sense so far?
No, I'm following you 100%.
Okay, so the idea is, I mean, at least this is my read of it. It's the same old paradigm that we used to use for translation, where you have an LSTM to encode something, then you attend it, then you decode it using an LSTM and you make your predictions. But instead of using LSTMs, because they're so computationally heavy, use a form of intention that acts like an autoencoder instead.
Yep.
Now, just as a side coder, what an autoencoder is it's something that takes your input and just reproduces it. But the intermediate step is quite information dense.
So do you have these self-attention you said before?
Yeah.
On your inputs and your outputs?
Yeah, that's the encoding step now.
And both of those are autoencoders.
Well,
that's doing autoencoder-like work.
It sort of is, because you're really just reproducing what you saw using a compressed representation.
Right.
And that compressed representation is handy.
Yep, I got you. So sorry, just to interject again. Okay, this might be, I don't know if this is messing up with your explanation, but like, so you've got your self-attention on the input and your self-attention on the output.
Yep.
And I think, I know you explained this at the start, but like, is there some kind of, what's the sort of like error between the two? Does that make sense?
Yeah. So error with respect to what, I guess, is the question.
I guess the input is like, I don't know, a sentence.
Yeah.
And the output is like, I'm just gonna paraphrase what you're saying to me and see what I've taken in so far. Pretty much like, if you say the cat sat on the mat, the cat is like encoded in the. Is that right?
Well, the idea is that, and this sounds really dumb.
No.
Everything is encoding it in everything.
Yeah. Okay.
So the idea, like with an LSTM, you kind of get a relationship between elements in your sequence that are really far apart, right? That's possible.
Right. Yep.
But there's a lot of intermediate steps in between.
Yep.
With attention, or like this kind of multi-head attention that we're using in order to do autoencoding, you directly get a relationship between each element of a sequence and every other element in the same sequence. And that tells you, well, over the course of training a model, you start to see how closely related those things are, and that becomes important information.
Right.
So, yeah, the idea is that where once you started out with, say, just an element of a sequence, which is the word "the" turned into word to vec or something similar.
Yeah. Okay. Yep.
Now what you've got is still a set of numbers, but it's kind of been mixed with every other word to vec encoding for words in that same sequence.
Yep. So is it kind of like more of like a richer way of encoding information?
That's part of the appeal, yeah. In addition to the speed thing, because like I say, with an LSTM, you might be able to find, using an LSTM, the relationship between element 2 and element, 50-something of your input or output sequence.
Yep.
But because it goes through so many intermediate steps in between those two things, so you have to process element 3, element 4, blah, 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 until you get to element 50-something.
Right. Yep. The cross product is just boom.
Yeah, it's just like there's a direct relationship between these two things. How big or small is it? And there's no middleman. And that kind of is better in some senses, aside from the fact that you can push all the dirty work off to your linear algebra software. Yeah.
So I still don't quite understand how sorry for my ignorance, but I guess it's one of the reasons for this podcast is to find out about it. But how are the self-attention mechanism for the input and the output, how are those two related?
Through the intermediate attention thing. So the idea is that you use this self-attention thing to create a better representation of the data you've got.
Yep.
Cool. You do that for both your input and your output, and then you use a third intermediate attention thing to marry those two representations.
There you go. Yeah, so I was missing. Yeah, okay. So it's just more attention.
Yeah, this is why I'm kind of convinced that a lot of the contribution of transformers is keeping an architecture that we were pretty happy with, which is like encode, attend, decode, predict.
Right.
And then just getting the LSTMs out of the picture. And like doing that in a way that conveniently also does provide a slightly better representation per sequence element. Yeah, and so insofar as that's the case, it's not that complicated. It's just all the history that leads up to it.
Right. Okay.
Yeah.
Cool. So BERT, that's a transformer. It's in the name.
Mm-hmm.
Is Elmo a transformer?
Off the top of my head, I can't actually remember, but I think so.
Yep.
There's a proliferation of these things. There's Elmo. There was another one called OMFit, which was also an attempt at creating a pre-training model. And now we've also got BERT and similar.
Yep.
Yeah.
Cool. And then GPT-2.
Yeah. That's obviously being looked at more in terms of its ability to create natural sounding language.
I think it's amazing, eh?
Yeah.
I don't know. Yeah.
But like all of it's kind of looking at the same general problem, which is the thing where NLP falls over with regards to some other parts of the deep learning meta field, I guess. If I can use that word and not sound like an idiot. Okay, so I failed. Anyway, so the problem with NLP is that we haven't solved pre-training or generalization in that sense yet. I went back and did some object detection stuff recently, and that's so much easier these days. What you do is you get ImageNet, like you download some weights, then you clone a copy of the darknet repo, preferably the Alexi AB one. That's my personal taste. And then you get some data and you add that to your pre-trained weightings, and then you hit start and go to the pub. And we're nowhere near that in NLP. Like we just aren't. We're still really caught by domain specificity. So if I create a model that's good for something that I'm working on, then it might be total rubbish for a different set of data just because the language that's in it and how it gets used is different, not least of which because it might be a completely different language.
There has been some progress with regards to transfer learning, though, in NLP, hasn't it?
Well, that's what a lot of this stuff is about. So that's basically what BERT's about. It's a serious attempt at Google trying to do that, like replicate that user experience where you download a model, it works, you chop off the last couple of layers and train them with something new to suit your specific problem.
Okay.
Like that's pretty much what they're getting at.
Yep.
If we could do that, then NLP would be A, much easier field.
Yep.
But B, there'd be a lot more things we're capable of. It's kind of interesting though, because having so much trouble with this one fundamental thing is precisely why we know about transformers in the first place.
Right.
So if NLP didn't exist and deep learning was mostly just object this, that, and the other, then we'd still mostly be stuffing around with convolutional nets, in my view. Like, not that that's bad, because they obviously solve the object detection and recognition problems quite nicely, but the fact that transferability in NLP is so hard is kind of why we're getting some of this weirder stuff.
Cool.
And so that's good and it's bad. It makes it harder to do your job as an actual NLP practitioner.
Right.
That's just true. But on the other hand, it's leading to some reasonably interesting research. Yeah.
Yeah, sweet. Question that popped into my head when you mentioned about the hype around BERT.
Yeah.
Like, so to get to, so I've just to backtrack, like I've got a bit of experience doing work with NLTK and Spacey.
Yeah.
So those are some toolkits that you can use.
One of the founders of Spacey is actually from here in Sydney.
I did not know that.
No, he's not here anymore. But he used to be. It was this guy called Matt Honnable.
Oh yeah.
Yeah.
There's a lot of good things come from here. It's actually kind of surprising.
Yeah, it is.
But with regards to BERT, so I mean, Spacey and NLTK are just two toolkits that you can use.
Yeah.
How does BERT sort of slot into the tool bag if you want to, I don't know, take this and start using it tomorrow?
Well, I mean, it's not supposed to slot in. It's supposed to be a tool. Well, no, that's the reality. Like, it was an attempt at being a tool bag in its own right.
Right. Because there's a lot of hype around it at the moment. Everyone's, yeah.
Yeah. I mean, it's not entirely justified. They're claiming some new benchmarks for various things. And like, insofar as that's the case, yeah, cool.
Okay. Yep.
There's another question about those benchmarks themselves, but different issue. Yeah, I don't know. So one thing I ran across recently was I was working with this one particular NLP package, which I won't name.
Okay.
And I discovered that I could get the same performance out of something much simpler. Now, is that a good thing or a bad thing? So, yeah, I mean, like...
Do you use a random forest or do you use a neural network?
Well, I mean, one way or another, someone's actually got to check, does this work? And insofar as that's the case, excellent. Mm-hmm. I'm glad somebody's done that. And it's kind of the same with BERT. Like, not all of us have the kind of compute needed to build that, or the data, in fact.
Yeah, true. Okay, so that's some new stuff I didn't know. So for BERT, you have to have a lot of data.
Well,
is that a tick?
If you wanted to build it from scratch, you would. The idea is that if you want to use it on something...
Say I wanted to use it on that little like MacBook Air over there. Is that even possible?
I don't know. That's an open question. If you want to stand on the shoulders of BERT, it's possible. And that was kind of the idea. Like, you should be able to learn this into something that suits your ends. If you want to build it from scratch, that's a lot harder. But the whole point of BERT is that you shouldn't need to do that.
Yep.
So in practical terms, it can be useful. We've tried it around the office on some stuff, and it has kind of shown promise.
Cool.
In the end, we didn't wind up actually using it because we found something simpler that worked as well or better. But that doesn't take away from the existence of BERT, in my view. Yep. Someone still needs to have tried that and checked, does this work?
Okay. So I guess again, this is my naivety because I haven't played around with it yet. But again, what are like the use cases for BERT? When would I pull it? When would I roll it out onto the battlefield to like try solve something?
Yeah, I mean, theoretically,
particular problem
NLP rated,
like like word to vec, you can like you convert your sentence into into a vector or whatever, and then you can manipulate that through classification or whatever you want on that. So how does BERT fit into that picture?
Like what you've just said then is basically the classic use case, because what BERT can do is take an input sequence of tokens or similar and provide a representation of the sentence as a whole. And so if you go and get it, in fact, part of the code you get is this ready-made server where you can point it at a BERT model and it will act as an API. So and then it also gives you a client for talking to that API so that you can have a sentence, send it off to this service, and it will send you back the vector representation of that sentence as a whole.
Okay. Can I, sorry to interject again, but like bringing this back to our discussion right at the start, like, is it safe then to say that BERT is like a better way of, a more meaningful, deeper way of representing sentences than say word to vec? Is that a safe thing to say?
I mean, like, yeah.
Okay.
So insofar as some of the stuff BERT does, word to vec couldn't necessarily be said to do. Yeah, sure. Whether or not you need that extra layer of complexity for a task you're working on is a different question.
Exactly. Yeah.
So like there can be situations where, so one of the things that BERT is really, so BERT's not proud of achieving it, the researchers that built it up. It's not anthropomorphized the model. That's a really common failing of machine learning people.
Yes.
Anyway, so one of the bigger achievements of BERT is that it's capable of resolving the problem of polysemy.
Okay.
And what that is basically where a word can have different meanings depending on context.
Right. Yeah. Right.
So the word right is a great example. So it could mean correct. It could mean this
Right.
hand over here.
Yeah.
Or you could talk about like righting a ship
Okay.
or righting a wrong.
Yeah,
And
right.
that means correcting something. So which of those meanings is the important one? With word to vec, you can't get that. There's only one embedding for a given word. Right?
Mm-hmm.
So you're kind of blind to that problem.
Right.
But with BERT, because it's a distributional representation, you actually stand a chance of working out what specific embedding for the word right you want to use depending on the context.
Yep.
So that's a problem it solves that Word2Vec simply doesn't. And if that's important to you, then yeah, BERT is a step in the right direction.
Okay.
And it can be, especially on things like social media.
Okay, cool.
Yeah.
So cool. This is awesome. Some questions I have for you that weren't on there that have sort of come into my head.
Oh, good.
is okay. So there was recent. I think they used transformers in the recent Alpha Star StarCraft thing, which I've had a little bit to do with. Yeah. So I can't remember just off the top of my head the name of the researcher, but they realized that, like, sequence modeling is like a large part of playing StarCraft or whatever. And then they treated StarCraft as, like, essentially like they took their natural language processing ideas and applied it to StarCraft. I don't know. If you got anything to add there, like,
well, I mean, like,
do you think that's a good way of doing it? Like,
yeah, of course.
Yeah.
Like, a sequence-to-sequence problem isn't confined to natural language processing.
It's amazing.
It's just a field where we keep, like, kicking rocks over and finding a sequence-to-sequence problem underneath. So there are examples out there of people using transformers on time series data, so like electricity load or similar. And there's no reason it shouldn't be the case for something like a reinforcement learning setting too, because it's still a sequence of actions. And insofar as you've got a sequence of input actions, then a point where that stops, and after that you've got to predict another sequence of actions. That's perfect. That's perfectly the use case. And so, like, yeah, that's a really natural adaptation. And if transformers work in that kind of agent learning field in a way that is A, fast because it's all matrix multiplication, and B, maybe makes things a little bit more, not that they aren't already, but a little bit more explicable, because you can interpret the matrix of attentions to try and see, like, what relates to what a bit more.
That's awesome.
Yeah, so, like,
That's really cool, actually.
yeah, I mean, there's some fun to be had, because, like, maybe I built a pylon X actions ago,
Yeah.
and I can see that relates strongly with, I need to build something else now, like a gateway. And so you can start to, with some effort, back out the actual reasoning.
Yeah.
And that's a really nice and, above all, graphical way to do it, because we all know people like nice shiny graphs. So yeah, like, attention and transformers more generally. Actually, no, attention is the general thing. Transformers is the specific thing. Let's just forget that. Yeah, transformers. Transformers and attention more generally are actually kind of suited to this world, because, yeah, you've got a sequence of actions, which is your input, and that's the past that has happened. And now you've got to make predictions about what's going to work in the future. And not just one step, but a lot of steps potentially. And that's the perfect sequence-to-sequence learning case. So, yeah, I'm really glad to hear that someone actually tried that.
Yeah.
And kind of got somewhere with it.
It's, yeah. And I think I've also seen a couple of papers this year, similar sort of ideas, sequence to sequence, being applied to robotics.
Yeah.
Same idea. Like, you got your set of actions and, I guess, try to predict the next set or whatever.
Yeah. Like, the conceptually speaking, the only thing you've really got to take care of is that the state vector at each point in your time series is probably pretty complicated.
Right. Right.
But then there's an intention layer to kind of take care of that.
There must be a ways to even like interpret, if you can, I don't know if Lime could do that, but something, you know what I mean?
Well, theoretically, Lime can interpret anything.
Yeah. Yeah.
I mean, not to sound too sarcastic, maybe it can, I don't know. But probably there's a fair amount of mileage to be had from just inspecting the attention matrices that you get when you're predicting something and seeing what that tells you. Yeah.
I mean, like if the purpose of this podcast was anything, you've sold me on Transformers. I think I'm going to have to go and spend some time now.
I mean, I was
having a play.
Yeah, they're conceptually not as complicated as they look. They are still complicated, but they're not that big of a problem that you can't work out how they work. And they do stuff quickly. So, yeah, I mean, everyone should have a crack. Why not?
All right. Next thing that I'd like to talk to you about is, I guess, the field of NLP.
Yeah.
Where it's at. I think we've already spoken a lot about where it's at this point.
Yeah.
So, I mean, you know, there was Wörterwerk, now Transformers. So where you've already suggested a couple of things on this podcast actually on like things to explore.
Yeah.
But where do you see the field going in the next, let's say, 5 years?
I
know.
So I'm going to have a crack at answering that.
Yeah.
And I can't wait to see how badly this answer ages. One thing I'm reasonably confident about is that languages other than English and maybe Chinese that have lots and lots of resources will start to become more important. I think the reason they aren't at the moment is not because there's necessarily an absolute lack of data in, say, Indonesian. It's just really fragmented. It's not gathered together in one nice big monolithic corpus that's beautifully labeled and had data quality on all of it.
Just to interject, what do you mean by more important?
Sorry, what was I saying when I said more important?
You said like languages like, I don't know, in Indonesian will become more important?
Well, I mean, yeah, so we're capable of doing a lot of really complicated and interesting things in English at the moment.
Yep.
But when you try it in another language, some of that just kind of falls over.
Mm-hmm.
I think figuring out some of the stuff that we can do right now in a language like English or Chinese, and spreading that to other languages would actually teach us about the problem itself, because solving a problem in a language agnostic way is, at least in my mind, invariably different to how that works when you only have to worry about one language. And so, like, I spent a fair bit of time today talking about how BERT's actually pretty good, and GPT-2 and similar. But in some senses, a lot of these things are basically taking something that we've known as a framework for a bit, making it work a bit faster, and then throwing quite a lot of compute at it.
Mm-hmm. So you think the compute hypothesis, I think is what it's called, where you just throw compute at algorithms and scale them. You think that's going to be the future of the next 5 years?
Well, not necessarily, because like I was saying, I find stuff that's simpler and works just as well. So maybe the compute wasn't necessary.
Yeah.
And this makes me think that we're missing something. There's something that, like, this is just me being a conspiracy theorist. There's something that we haven't quite understood yet. And instead of figuring that out right now, what we're doing is making existing stuff work better with compute. And that's good, because we're still finding things out like how transformers work. Yep. Like, that is actually a big step forward. But how do you deal with language modeling and language problems more generally, or at least make them work to the same level across a number of languages?
Right. So if I was to use an English BERT right now, I couldn't use it on Indonesian. and like, there's no transfer learning.
Well, probably not. Like, there's arguments to say, yeah, you can. Like, maybe you could transfer it with a slightly different vocabulary and whatnot, because perhaps Bert's learned some sort of internal state that figures out how grammar works. But beyond even that, beyond even transfer learning, like, how do you address a problem in a way that works equally across a number of languages? I think that would tell us a lot about the problems we're trying to solve in NLP. And I think that's kind of an open expanse at the moment.
Okay.
So people that are looking at that kind of problem are ones that I kind of watch closely at the moment. The problem is it's not the easiest, because some of these languages, even though they've got tons of speakers, like Indonesia's got like 250 million people.
Yeah, it's insane. It's insane.
Big.
Yeah.
But there isn't necessarily a huge amount of data to work with. Like, there's some. But going from something that can work on English by virtue of the fact that there's so much compute, that the fact that you've got this much data doesn't really matter because there's just tons. Like, my guess is BERT might not work as well in Indonesian, though I'm happy to be proved wrong on that. And then there's like even the more extreme case. So a friend of mine, he's over at Stanford now, and he's working on really low resource languages, which is actually Aboriginal languages.
Awesome.
Yeah, and that stuff's really interesting.
Yeah.
So, I mean, without wanting to sound like Noam Chomsky, how can we look at solving a problem in a way that is more language agnostic? Yeah, I think.
Yeah, that's nice, man.
Yeah.
I see. Yeah, I see where you're going with that. Yeah.
Like, not because solving that is cool, but
it's
because
the greater sort of the greater mystery that we haven't understood yet.
Yeah, I mean.
Yeah. No, that's cool.
That's what I.
Is it? Yeah. Do you think there's any other low hanging fruit? Like you mentioned, looking at looking at what the transformers are doing. Is there anything else along those lines that you think could be like potential boom areas in the not too distant future?
Like,
so interpretability would be one there, I guess. But
none come to mind immediately, but given that we're solving a lot of our problems by overwhelming them at this point, probably not. I mean, maybe there are some, and if they exist, at this point, it's probably because nobody's thought of it, and it was just lying in plain sight. So maybe there are some low-hanging fruit out there, but yeah, scratching my head right now.
Okay.
I'll actually physically do that. No, I can't think of any.
Okay.
Yeah. Like another giveaway is that the sort of problem we're trying to solve now is getting more and more complicated, like entailment. So you get given two sentences, like, I went to the bar and the bar had lots of people in it. That should imply something like sentence C, which is people go to the bar. That's normal.
Right. Yep. Got you.
So people are trying to solve that problem now with varying degrees of success. And that's not, there's no simple way to handle that problem, I think. And given that our attention's turned to something like that, yeah.
Okay. Which kind of takes us on to, quite naturally actually, onto the next kind of...
Naturally?
Yeah, quite naturally. Onto the next topic I'd like to talk about, which is, I guess, like the link between intelligence itself and language.
Okay. Man, that's philosophical.
Yeah. So, like, I don't know, like Ben, you know Ben.
Yeah.
I pointed out the other day that, like, there's something really strange going on with GPT-2. Even like when you scale it, like I don't know, I want to use this term loosely, like the intelligence, air quotes right now.
Yeah.
that it seems to exhibit when you scale it up.
Yeah.
And it seems to be capturing there's something there that we don't quite understand yet. and I don't know. It's
Yeah.
So link between intelligence and language, I guess.
It's complicated. Like I vaguely recall reading something maybe in the last couple of years that suggested the biggest neural networks we create now, and I mean like sitting in a server farm somewhere, that still has less capacity as measured by neurons, and that's not necessarily a good measure of capacity, than a fruit fly.
Mm-hmm.
So
yeah, I know.
We've still got so long to go before we're creating something that's as big as a human brain. But
Ray Kurzweil, 2030.
Miles Bennis Dyson, like 22 years ago, whenever August 97 was.
Sorry, who is he?
That's a Terminator 2 joke.
Oh, okay.
Yeah. I think it was the 21st of August 97 that Skynet was supposed to come alive.
Yeah.
Anyway, yeah, so I mean, is this real? Is it actually intelligence, or is it something that looks similar? I'm still on the side of it's still a simulacrum of intelligence as opposed to the real thing. But it's pretty good. Yeah.
Yeah, fair enough.
Like that's my off the top thought.
I mean, like, I asked that question to you because you've had a deep dive play with this, so I think it's fair to hear what you have to say. Yeah.
Thanks. So, I mean, just to like peek behind the curtain a bit, the original question we were talking about was like, do you think we need to get as far as artificial general intelligence in order to have a meaningful conversation with a computer? And stuff like what Talk to Transformer does suggests maybe not. And there are companies around Sydney, in fact, that are kind of working on this problem. So you can ask a machine, air quotes there, something about your data, and it can interpret what you're saying and then give you an appropriate response. Is that a meaningful conversation? Well, like, that's kind of in the eye of the beholder. So yeah, I don't think we're at the point where we have created intelligence in our own like. And one other thing that I'd like to point out and reinforce, in fact, is that a common trap that a lot of people fall into, and it's easy to fall into when creating machine learning models, is anthropomorphizing the thing.
Absolutely.
And thinking about a machine as if it works in the way the human mind does, even if like there are very respected people out there who have kind of talked about how neurons in a neural network work in terms of how the brain works. That's ultimately still not what it is yet. And so this kind of gets funny if you actually fall into that trap when you're building a model, because then it'll do something that isn't explained by how the human brain works. And then this kind of completely throws you off in terms of, what do I do next? How do I make this thing work better? So I'm still quite firmly of the camp that whatever GPT's doing, it's not conscious.
Oh yeah, I'm sitting in that camp too.
Yeah. And insofar as that's the case, I don't think it's intelligent in a sense. Don't at me. Yeah, I think if we want to talk about intelligence, that we kind of have to talk about consciousness as well, and models aren't that. Yeah.
I think consciousness is a whole nother conversation.
yeah, right.
I personally, I think that there's just my personal 10 cents is that there's definitely a strong link between language and intelligence. It's definitely one of the axes, if you want to think of intelligence as a multidimensional thing. I think language is definitely one of those things.
You mean like in an individual person?
If you, I don't know, like if you want to try quantify what intelligence is itself.
Yeah, I mean, like we know that we're not the only animals on Earth that communicate with each other in some sense, that are like able to I mean, even if it's just a warning cry.
Yeah.
Yeah, so like being able to form a society and have some sort of information flow between the members of it is like obviously some sort of sign of intelligence. Where you draw the line exactly is like up to the scientists, I guess. One person, I can't remember who it was, described language to me as a mechanism for shared attention. So it helps you and I think about the same thing at the same time.
So this is a different form of attention to attention we're talking about at the start of this podcast.
For the sake of clarity, yeah. But also, is it really so far-fetched that those two concepts actually share the same name? Like, the reason we're talking to each other here is explicitly to share information, right? And the medium we're doing that in, or the medium we're using to do that, to be specific, is language. And so insofar as that lets me know more than what I already had in my own head, does that allow me to reach greater heights of intelligence? Well, maybe. Yeah. So like, I don't know, that's kind of, I wish I'd done more studying on this subject. Yeah, but that's kind of my hazy view of things. Like insofar as there is a link between language and intelligence, I think a lot of it is explained by the fact that it lets you see through someone else's eyes.
Language does.
Yeah. Yeah.
Well, yeah, I mean, in a way, yeah. Like, if I could just, using language we just used right now to understand what you just said to me, I don't know, you can send instructions to people and then see through their eyes, in a sense.
Yeah. And you wind up knowing more than you did originally, hopefully.
Yeah, true.
Maybe not if you're stuck in an echo chamber on social media, but like perhaps the rest of the time. Yeah.
All right. So to bring this back to the real world.
Yeah. Okay. Why not?
So talking about all this, there's to the practitioner out there, the people in industry that are looking to use these techniques. And by these techniques, I mean natural language processing techniques like transformers, BERT, Spacey, etc. So, does any of does any of the stuff matter?
Like, should this matter to someone who's a data scientist in a company somewhere around the place? Yeah, sure. One of the reasons I'm going to go back in the past again. So my career got disrupted before it even started by NLP, which is a really Silicon Valley thing to say, but anyway. I originally wanted to be a translator and interpreter. And then just before I graduated, I'm not joking, it was like 2005, 2006. Yeah, I'm old. Google Translate came out. And I kind of saw the writing on that particular wall. It's like, if they can do that, then like they're going to come for the rest of it. So I wound up being an economist, which is kind of the same thing. Because instead of using what people say to understand how they tick, you're looking at what they do in order to understand how they tick. And I went from there into the corporate sector. And when I got there, I wound up in this call center actually for a really large company. And the interesting thing about a call center is it boils down to people talking to each other all day, every day. Like there's just gigantic oodles of this natural language data. And I'm firmly convinced that a lot of companies are like that because every single company is run and operated by humans. So like at every company you go to, you can pretty much count on there being some sort of natural language data somewhere. It's hard to think of one where there isn't. In fact, I can't off the top of my head, just because companies are made up of humans. And insofar as that's the case, yeah, NLP might help you do something useful for your company. Even if it's just a more accurate...
I think it's a really good way of framing it. I mean, if there's language involved.
If there's humans involved, there's language involved.
Exactly. Yeah, and then NLP can extract something out of that and do something with it.
Yeah. It might not be like turn your company upside down. The thing I did when I was working in that call center was really just using NLP, a more accurate characterization of what was going on. Without getting into too many details, what was happening when I joined was people were reading notes left by agents one by one in order to see, like, why do people call us? What can we do about it?
Right.
And so doing something else to make that work on all of the data you've got available actually gives you a completely different picture. And that then becomes something that you can act on.
Yeah, that's awesome. That's actually really cool. Yeah.
So it's. I think it's probably the same for a lot of people's companies. If you dig around, you can find some sort of natural language data set, not necessarily in a call center, but something similar, that helps you, if nothing else, characterize how your company actually works and what it actually does. And that knowledge is actually really useful. So by virtue of being a lapsed economist, I happen to know a few people who work for really large banks and the central bank, in fact. And for them, a really important problem is actually working out what is the economy doing right now. So,
right.
Yeah, that's actually really hard. Working out what happened 3 months ago, that's kind of possible, but that's old data. Working out what is going on right now in an economy of like 25 million people, which is what Australia is, that's already really hard. But doing something similar for an even bigger economy is correspondingly hard. But it's still kind of important information just to know how are things working right now. In fact, it's really, really valuable information. Hedge funds will fight tooth and nail for it. And it's the same. It's the same if you like get a gig, go into a company, and use their data to just come up with a better way of explaining, well, we know what all the processes are and what the rules are for how things should happen, but what really goes on here? That's actually really valuable. And natural language processing can help you get there, just because in any company, there's going to be some of it lying around.
Yeah, for sure.
Yeah.
100%.
So like, yeah, I think all this stuff is like...
So the writing's on the wall.
For what?
You said it when you saw Google Translate come onto the scene.
Yeah, I mean, it might not be on the wall for everyone. I'm not in the camp that suggests that everyone's going to lose their job from automation. I think,
Sure.
So, like, some people's lives are going to become harder. Yes, that's why I didn't become a translator and interpreter. Some people are not actually going to experience any change because basically what automation is you replace labor with capital. And there can be situations where that's actually uneconomic. And so the automation doesn't happen. Like, it is better off, like the company is better off in the long run to just leave a human doing it in some cases. And so automation won't necessarily touch everything, but there can be some things where it will. And natural language processing is a really big part of that. Yeah.
Awesome. I like your economist take on it.
It's fun because in this whole field and in like machine learning in general, a lot of the time what you're doing is finding a way of getting something to create an accurate characterization of what people say or do and why. So you're trying to forecast the number of calls into a call center. That's exactly a situation where you're trying to do that. You're getting a model to come up with some reasoning behind volumes for calls. It's the same thing over and over. And so spending time thinking about why people make their decisions is kind of not wasted time in that regard. But like, that's just my view as an economist. I'm probably pretty biased. Other people come into data science with wildly different fields and find that it helps them a lot. That's just kind of worked for me. Yeah.
Cool. All right. So you're going to be running a little mini conference soon?
Yeah. Thursday night, this week, Sydney NLP is going to be running an event at the Tyro FinTech Hub. Thanks very much, Sharon Liu, for hosting us as always.
Shout out to Sharon Liu.
Yeah, and the Tyro FinTech Hub. They've been so good. Basically, the idea is that ALTA, which is an Australian Linguistics and Technology Association, that's not precisely the name, but that's what it is, has a conference where people who work in industry and academia on the field of NLP can basically talk about what they're up to. And we've been lucky enough to get a couple of people that presented to that to agree to run us through what they're doing. And so there's some pretty interesting stuff. One speaker is going to be Xavier Holt, who works at a regulatory technology startup called SIFT. This is a perfect example of what I was talking about when I said there's natural language everywhere. So what his company does is works on receipts and processing them in a way that makes that data more useful. And then there's also another person, Hania Puschi, who works at Channel 9 now. And she's got some pretty interesting stuff to say too.
Awesome.
Yeah, so we're really looking forward to it. We've got about 70 takers so far, but there's still room.
If people want to find out about your meetup, how can they do that?
Yeah, it's the classic go to meetup.com.
It's Sydney NLP, is it?
Yeah. I can't remember what the name exactly is these days. It's like Sydney NLP Society. Or Sydney Natural Language Processing Society. But yeah, you type in Sydney, you type in NLP, you'll find us.
Yeah, okay, cool. All right, well, Stephen, it's been a pleasure, mate.
Yeah, me too. Thanks very much for having me on.
And maybe do this again sometime, eh?
Yeah, that'd be great.
Awesome. Cheers, mate.
Thanks very much.
Hi, everyone. So yeah, if you enjoyed this podcast, please help us out by, liking, clicking, or subscribing to your favorite podcast provider. That would definitely help us out a ton. Cheers, and see you guys next time.